start the screen here. Last time I introduced you to the different type of losses for a switch, right? We have the static loss and then the switching loss as well as the driving loss, right? And this chapter will focus on switching loss more so than the other two. And it's always, in my mind to expand this chapter to include not just switching losses, but also driving losses. Static losses, you learn it from EE411, right? From the waveforms, right? Current waveforms that you learn in EE411 through the switch. And then you do RMS square times RDS on for a MOSFET, for example, that gives you the static loss. The two that you have not learned is the switching loss, which are the switching losses and driving loss. So at this point, I only have switching losses for this book, and hopefully in the future, I would also include driving losses. Okay. All right. I believe this is what I covered last time, right? Switching in real world does not occur instantaneously, and in majority of our of DC to DC converters, we implement hard switching. I talked about this last time, right? Another name for hard switching is square wave switching. You can see the shape. It's a square wave type of switching, right? And you can see if you look at these waveforms, this is coming from I believe LT1170, wasn't it? Yeah, LT1070. And you can see that we have, because I'm zooming this out, you can see that the transition is fast, right? Really fast, relatively speaking. But later on, we're going to zoom into these transitions. And you'll see that, even though relatively is fast, but they're still overlapping, overlapping waveforms between the voltage and current. All right. Again, red here is voltage, as I mentioned last time. Blue is the current. So obviously from those, we know that this must be turned off right there, and this must be turned on transition. All right. Okay. And then here is a simulation of close to ideal switch. This is the one that was used in E410, right? S break. We use this in OrCAD PSpice to model very close to ideal switch. And then I'm also using a real model of a MOSFET, IRF 150. Anytime you see IR in the name, that means this comes from this manufacturer called International Rectifier. So it used to be big in MOSFETs. But that company now is being bought. Now is part of a bigger company called Infineon. So there's no longer International Rectifier. Now they are part of Infineon. But they still keep these part numbers. So you still see MOSFETs that begins with IR, prefix IR, IRF. So if you see that, that means originally came from International Rectifier. All right, so that's real model that I found in OrCAD PSpice, and what I did here, I'm turning on and off these switches, so you can see the difference between real world, not real world, but with between the close to ideal switch versus a switch that has real world model of the MOSFET. So these are the differences you can see from the waveforms. Right here. Let's see, turn on transition is up here. You can see this S break is very fast when you turn it on, right? Almost like a square wave, right? And then you can see for the MOSFET, when you turn it on, you see it takes time to turn on, right? Why? Because there are parasitic, right, components inside the MOSFET. So if you look at the real model, the model of this MOSFET, there are components inside, capacitance, inductance, resistance, what have you, right? And so that's why it takes time for this MOSFET to turn on. It's still fast, right? Relatively speaking, if you can see the time here, it is still fast, right? Microsecond type of transition. But nevertheless, no, doesn't matter how fast it is. The point here is that it is not instantaneous compared to the close to ideal switch, which is the S break that I use in that simulation. So that's turn on. Turn off is the next waveforms right there. Right, same way. If you look at the S break transition, right, it's really fast, like a step, right? Jumps from high to low real quickly. Whereas the real model, the real model of the switch, IRF switch, you can see it takes time, right, to turn off. Okay, still fast. Again, if you look at the time value right there, the axis, it is still fast, right? Microseconds, or maybe nanoseconds, very low microseconds looks like. And you can see that even though it's fast, if you zoom in, it is still going through this transition, right? It is not instantaneous. So that's the point I would like to show you, is that real world MOSFETs, or in general, real world switches, will behave the same way, right? It takes time to turn on, and it takes time to turn off. And for this reason, in E410, I ask you to use S break, right, for several experiments, so that you won't have to deal with this kind of a headache, right? Because there are implications from these transitions. All right. So that's current. This is sorry, that is that current? Yeah, these are showing you current. So you can see current transition, turning on and turning off. The next two sets are for voltage. Same way, right? You can see voltage transition when it's turning on, right? When it's turning on, so we expect the voltage to change from some high value to low value, right? When it's turning on. But again, for ideal, it's quick, very, very quick for S break. For MOSFET model, it takes time. Same way with turning off, right? You see that, right? It's a jump for ideal switch, and it takes time for the real model of MOSFET. Any questions on this? Again, the idea behind showing those examples is to demonstrate that the actual switches will take time when it's turning on and off, both in the with respect to the current through the switch as well as voltage across the switch. All right. Now next, I'm using the same example that you saw earlier with LT1070 from this picture right here. Where is it? Right there. Right. So this is the zoomed out version of the waveforms, right? During the transition, you can see they're quite fast, right? But if I zoom in to any one of these transitions, then you'll see the overlapping behavior between the two waveforms, between voltage and current. And this is what I'm showing next, right here. Okay, this is turning on, looks like as blue is current, red is voltage, right? So when I'm zooming in, when I zoom in, clearly you can see the overlap, right? That it takes time for these MOSFET, and again, this is coming from 1070 chip. The MOSFET is internal to that chip. So in that model, they put real model of the switch inside the IC, inside the controller, right? So again, just like we are expecting, it takes time for voltage to drop from some high value to low value. And then current will do the opposite direction, right? Because it's turning on. So it goes from 0 off to fully on, right? Now, another thing that I would like you to be aware of this situation, be aware of this waveform, is that the overlap right there, right? And that is important to observe. Why is that? Because then we have a segment of time, we have some amount of time where the switch is still going through the transition, right? Because they're not instantaneous, right? What I mean by that is that there is the switch takes time between two static conditions, right? What I mean again, this means that before I turn on the MOSFET, right? Hang on. If I turn on the switch, you can see that the switch was in static condition right there, right? Where the voltage is flat, the current is flat, right? That's current is flat, voltage, oh, sorry, that's voltage across the switch, right? That's static condition, meaning it's constant, and current is also constant, right? And then toward the end, or after the transition, you can see that the switch reaches a different static condition, right? So you have the new I switch prime, and then the new voltage across the switch prime, right? So you can see that we have two different static conditions before and after the transition. And so in between, this is what we call the transition, right? Switching transition. Okay, and the two static conditions are different, right? Before and after. You can see that before switching voltage is high, voltage across the switch is high, current through the switch is low. But then after the transition, you can see the opposite is true, right? That switch current is high while the voltage is low, right? So again, our focus is on the transition, the segment of time to go from one static condition to the next one, okay? And during this transition, you can clearly see there is an overlap, right? There is an overlap between voltage and current. You agree with that statement? Yes? So if you agree with that statement, that means we have a problem, right? Anytime you have an overlap between voltage and current, what did I say in EE411? If voltage meets current, right? They fall in love and they got married and they have a child called, what's it called?
Power.
Power, yes, power. And so this power, right, occurs for delta t, right here. That's delta t during transition time, right? So you have overlapping between voltage and current, right? That's instantaneous power, right? That's P, V times I, V times I, V times I at any given time during the transition, right? And so, so this power, right, occurs, right, for delta t, right? So that gives us what we call energy, right? P times delta t, right? So this is the energy that we sacrifice, basically, right, to do the transition. This energy is not the energy that it is not energy that is being used by our load, right? Because this converter has a load, right? And so this power, because of the overlapping, produces energy, right, over time, of course, over delta t. And this energy, unfortunately, is not being consumed by the load. It's not being used by the load, right? So this is producing, or this translates to what we call power loss, right? And so that's the problem that I was referring to, right? Anytime you have an overlap during the transition time, doesn't matter if it's turning on or off, then we are dealing with what we call switching loss, right? One from turn on, the other one from turn off. I'm hoping that the next, I have another picture, maybe, hopefully. Yes, so this one must be turned off, right? You can see another overlapping, right? A transition time between two static conditions, right? There's the first static condition and there's the second static condition. So it takes time for the switch to go from first static condition to the next static condition, right? And that time is delta t, is called to, that delta t time is called transition time. Or in this case, because it's turning off, we call it turn off time, right? To be more specific. The previous one is called turn on time. This one is turn off time. And again, you have the overlap between the two. And as I said earlier, if you have an overlapping waveform between voltage and current, then we got problem, right? We got power loss, right? And if you multiply that by delta T, then we have energy that is not being used by our load. So that's not good, right? As you learn from EE411, we want all the energy supplied by the source to be delivered to the load, right? So here's a portion of the energy from the source that is not being used by the load, right? Okay, so that translates into efficiency, right? The more overlapping, the worse, the longer the time, right? Here corresponds to the bigger the loss, right? So, or also the more overlapping you get, the more loss you'll end up with. And at the end of the day, you get less and less efficient converter, right? So that's why switching losses is an important aspect of DC to DC converter design, right? When you're designing DC to DC converter, you want to make sure that you can minimize switching losses, right? How? We're going to learn that in this class. Any questions so far? Oh, right here actually. Is it the one? Yeah. So these are the different methods to reduce switching losses. Conduction losses may be minimized by careful selection of components. This is part of EE411, right? By knowing the a better component to use, you can minimize conduction losses. But in this case, or in this chapter, we focus more on switching loss. Per given switching frequency, switching losses may be minimized by careful selection of components, using auxiliary circuit in hard switching topology, and using alternative switching technique. So I'm not going to go over the first one because I'm not an expert on this first one, right? That goes into device physics of the component, right? How do you design, a MOSFET, a better MOSFET, right? That's not part of this class. That's more like semiconductor physics type of class. And then what we are going to cover in this class is the one that's related to, more on the on the power converter side of power electronics, right? So we'll do additional circuit. We'll look into minimizing switching loss by introducing another circuit, an auxiliary circuit, right? And still you are using hard switching, PWM. That's the first method. We call this circuit snubber circuit. So we're going to do that in the following chapter. And then another method that we're going to learn in this class, one of my favorite topics for this class is this method right here. It's called soft switching, right? So why not use a different switching method, right? Why do we have to use hard switching, right? If this is the reason why we get the overlaps, right? Because you can see the overlaps happens because we do hard switching, right? But if we can somehow do the switching of do the transition, or not the transition, if we can somehow turning on and off the switch without doing it with PWM, without hard switching the switch, then we should be able to minimize the switching loss, right? In other words, if I could somehow reshape the waveforms such that they don't behave this way, right, to avoid overlapping of the waveforms, then that would be a good way, right? And that's what's called soft switching, right? So imagine if I'm able to do this, right? If I'm able to somehow wait until the current, is it current or voltage? This is voltage, right? Blue is voltage. Let me use blue then, so you won't get confused. So if you're able to do this, right? Somehow you're able to do this. So you not force, but the voltage naturally goes to 0, right? Like that, something like that. And then I'm going to keep the same current, right? So current is red. So you can see by doing so, I'll wait until the voltage across the switch naturally goes to 0, And then once it goes to 0, then I can turn on the switch. You see that? If I can do that somehow, then I could get rid of the overlap, right? Or minimize the overlapping waveforms, right? So that's the approach. Does that make sense, hopefully?
Would you like alter the voltage without like turning on, like wouldn't you control the voltage just using the MOSFET and it would just have its natural operating point?
Sorry, say it again.
So wouldn't like the voltage kind of be like the MOSFET would have like an operating point. So could you like control the voltage without altering the current? Like would you do it using something external?
Oh yeah, we could. Yeah, so we could turn on the MOSFET. You're right. We are in, the one who's controlling when the MOSFET is on or off. But the behavior of the voltage, right? The way the voltage shapes after you turn on the MOSFET, or current after you turn on the MOSFET, is a function of the components that you put in the circuit, right? It just so happened that for PWM, when you turn off or you turn on the MOSFET, right away, the current jumps. It doesn't have to be this way, right? If you can somehow still turn on the MOSFET, but then reshape the waveform such that it does not follow a square wave, then you could theoretically minimize the overlapping amount, right? So again, we do have the control over when to turn on and off the switch, but the shape of the waveforms, either voltage or current or both of the switch, could be determined by external components of the circuit. Hopefully that makes sense without going through the details of soft switching yet.
Oh, I got you. That's the soft switching's for later.
That is actually the concept behind soft switching, is that once you turn on and off the MOSFET, you introduce external components to reshape the waveform, voltage waveform, current waveform of the MOSFET, so that they don't follow square wave. Okay, so that's the concept behind the soft switching. Hopefully that answered your question. I'm not sure, but hopefully that answered your question.
No, that makes sense.
Okay, good. That's why I was saying earlier, if I could somehow reshape this voltage waveform to, it inherently goes to 0, right, before I turn on the MOSFET, right? So I can wait until this voltage across the MOSFET goes to 0, then I turn on the MOSFET, right? If I could do that, then theoretically speaking, you don't have any overlapping, right? Or very minimum overlapping. Again, that's concept behind soft switching. So we're going to talk about this wonderful technique. I can't recall which chapter, maybe chapter 4, right? That's why it's a very exciting technique. I really like that method. I get to use it actually at least once in my previous experience. I helped design a soft switching converter for medical equipment. It was a high voltage DC supply, 120,000 volts DC at 40 kilowatts. Especially for those kind of applications, you do need soft switching, because PWM is great, but when it comes to high voltage, high power, you're going to end up with lots of noise, lots of switching loss, right? Any other questions?
I had a quick question.
Sure, go ahead.
This is a little bit of a tangent, but in the MOSFET, like initial graphs, I noticed in the first graph, the current was leading the voltage, and in the second, the voltage was leading the current. Like they switched. I'm referring to the turn on and turn off graphs under figure 1-7.
-7. Oh, not that one. This one?
Yeah, that one.
Oh, okay, it's crowded here. Leading? What do you mean by leading there?
It's like the current change seems to happen before the voltage one. Like the current seems to almost steady state before the voltage
Oh, I see. This hopefully can be explained after we talk about snubber.
Okay.
It has to do with the path that allows to allow current to change first before voltage. In order for current to change, voltage has to stay the same because there is no other path for the current to for the voltage to fall. I know it's kind of hard to understand right now, but I think to answer your question, let's wait until we talk about snubber.
Okay.
All right.
Thank you.
Okay. You're welcome. All right. There you go. Yeah. Yeah, you can see it is true. Yeah, so that has to do with the path. KVL, KCL. That's another thing I like about power electronics. When you do the analysis of power electronics, all you need to do is KVL, KCL. Right? No fancy, no complex, theory that you learn in previous classes to analyze power electronics. You just need KCL, KVL, dVc/dt, LDI, LDT. Right? Mostly that's it. All right. Next, switching energy losses. So let's try to look into the equations of switching loss so that you understand the problem with PWM. So this is strictly switching energy loss in PWM, right? Sorry, let me take it back. So this equation applies for any switching method, but the equation that I'm deriving is strictly for PWM. So in general, switch loss consists of, or not switch loss, device loss, right? In our case, particularly is the switch, consists of 3 different losses, right? Static, switching, and driving loss. So I'm gonna ignore driving loss for now to simplify our analysis. I could simply add it, but right now I'm just gonna ignore it. And then these are the 2 big ones, static and switching. Static is, the equation for static is equal to the integral of I times B, right? So that's the mathematical definition of energy on the static, energy being used on the static condition of static state of the switch, right? Integral of P of T, right? B times I is P, right? So P times delta T, as I said earlier, that gives you energy. So that happens twice in a period. One is on time, the other one is off time, right? This is static, okay? This is when the switch is fully on, right there. And this is where the switch is fully off, right? That's why if you look at the equation for power inside, which is I times B, you can see that I here is I on, right? So that's the current when the switch is conducting, when the switch is fully conducting. That's gonna be practically DC current, right? Flat. Same thing with the residual voltage right there. So when the switch is conducting, right, we have a forward drop across the switch, right? And I know that's going to depend on the amount of current, but per given current, right, that forward voltage is going to be practically constant, right? Same thing with the off time. So when the switch is fully off, you have voltage across the switch that's going to be constant practically, right? And we're going to have some leakage current going backward through the switch. That's going to be very tiny current, but nevertheless, there's going to be a leakage current. And if you multiply the two, then you get static loss when the switch is fully off, right? So that's the first part of the equation right here for static. And I could simplify this equation using DC approach, right? And if you use PWM, right, like this, right, as you learn from EE411, the duty cycle is T on over T, right? This is the T on right there, and here's the T, right, the period. Right? So we know that duty cycle is equal to T on over T, right? And this portion of the equation up here, right? I can simplify that to be equal to T on, the amount of time the switch is on, fully on, times I on. As I said earlier, it's going to be practically DC, times B residual, again, practically DC, right? Plus the second portion of the equation right there, right? That's T off, the amount of time the switch is fully off, times I residual, which is again constant, and V off, which is also constant, right? Now I put approximately because if you look at the way I derive this equation on the next equation right there, I assume that that we don't have any transition time. So duty cycle is going to be just D, even though we know it's not going to be exactly D, right? Because you have turn on transition and turn off transition, right? But to simplify the equation, I'm just going to use D for T on, right? So D for T on is equal to DT. Sorry about that. Let me write it down. So from EE411, we learned that duty cycle is equal to T on over T. So therefore, T on is equal to DT, right? That's what you learned from EE411. But keep in mind that this is ideal equation, right? That would this equation was derived using, perfect or ideal square wave to define duty cycle, right? That's your T on, that's your T, right? But in our discussion here, we don't have a perfect square wave, right? Our square wave has rise time and fall time like this, right? So therefore, this equation is not going to be, the equation for duty cycle is not going to be the same anymore. However, again, I'm going to simplify the equation to ignore this rise time and fall time. And that's why I'm using this symbol, right, to, as an approximation of this whole thing. Does that make sense? Hopefully, right? So T on times I on times B residual approximately equal to duty cycle times T, right? DT right there. T on is DT. I on times B residual, and then T off, as you learned from E410, that's 1 minus D times T times I residual V off, right? So that's T off. As you learn from, again, E410, that T off, ideal T off is equal to 1 minus D times T, right? Again, simplifying the equation. Otherwise, if you want to derive it with more accurate equation, you're going to have to include what do you call it, transition time, right? So T switching on, T switching off into this equation. And since they are small in terms of value, right, percentage wise compared to, since this rise time and fall time is relatively much smaller compared to the actual on time and off time, I think this approximation is a good approximation to use. Okay. Any question on this? All right. So that's the first part of the equation for W static, right? So I just talked about W static. What about W switching? That's our concern, right? Switching loss. So switching loss, I'm gonna use the same equation, right? Switching loss is the turn on time, right? So that's different from the previous one. Right? Turn on time is the transition time, this transition time right there, right? As well as right there, the tiny time that it takes to turn on and off, right? So for on time, turning on time, again, you have the product of voltage and current. Remember the overlapping between current and voltage? You do the same thing here. You use the same equation, right? I times V, just like the static, same thing here. Turning off time, I times V during turning off of the switch, right? And this is something that I cannot simplify anymore because these are all equations that you have to write into the equations. So I of t is going to be an equation with respect to time. V of t is going to be an equation with respect to time, right? How do I know that? Well, take a look at this, for example. You see this? During the transition, you can see that current is a function of time. It's not constant. Same thing as voltage. During the transition, is not constant anymore. It is a function of time, right? So therefore, I'm not going to simplify that because that's going to depend on how the waveform is shaped, basically, right? Most most likely a linear shape. So if they are linear shapes, then you have to find those linear equations for the current and the voltage, and you plug those equations into here, and you integrate those equations with respect to time, turn on time, and you get the energy of that switching during turn on, right? So again, I'm going to leave it just like this. I'm going to call it W switching. I cannot simplify that again because of the fact that it would depend on the shape of the voltage and current through of the switch during the transition times. Are there any questions on why I don't simplify this further? Because this could be different functions for different switching, right? Different switches as well. All right, there's no question. Then how about power loss? We talked about energy, right? Energy during switching and energy during the static condition. Power loss, right, is related to energy, right? So power loss is equal to, well, first of all, you learn from physics that W, energy is equal to P delta T. And so therefore P is equal to W over delta T. But in our case, delta T is the entire period, right, of switching. So if we talk about switching loss, that means delta T is our switching period, right? So that's going to be T, switching, right? So then we know that frequency is the inverse of the period. So therefore, this is the same as switching frequency, the inverse of switching frequency. That's the reason why I have this equation right there, right? So for power loss, both for static and switching, it's just a matter of multiplying it by frequency or divide the energy by time. So either you divide the energy equation by time, by the period, or you multiply the energy equation by frequency, either way. All right, let's see what happens with our previous equations for static and for switching. For static, remember I simplify the static equation to this equation, right? From up here. Past. Where is it? So I simplify the static losses to be this one right here. So I'm gonna duplicate that equation right here, rewrite that equation here. Right, that's our static loss, right? And then for the switching loss, I'm gonna just use the same label, W switch, except now because we are looking for P, I'm gonna multiply switching loss, not switching loss, switching energy by F. So I'm gonna multiply switching energy by with frequency. For this, for the static, you can see that since I have D times I on times V residual plus 1 minus D times I residual times V off times, I actually skipped one step here, sorry. Let's see, you multiply by F, right? The original equation has T, I forgot, sorry. The original equation, let me go back to this equation. Forgot one thing. Let me erase this so you won't get confused. Okay, look at the original equation for W static. What do you see there? You see there is a period in it, right? There's a period in it. Let me use red. So that's the equation that I'm using for W static, right? And then there's a T for on, and there's another T period for off, right? So if I rewrite that equation here, imagine I use that equation here, then you're gonna have T right here and T right there, yes? And then since I'm looking for P loss, right? For P loss, you either divide the equation by T or multiply by F. So in this case, I'm dividing on and off by T. All right, so the original equation has T in it, but since I'm looking for power loss, I'm dividing each term by the switching period. That's the reason why the T disappears. Does that make sense, hopefully? Right? So now I have the equation for P loss for the static as well for the switching transition, right? So you can see that the equation, the simplified equation for power loss during static condition is duty cycle times I on times B residual, and 1 minus duty cycle times I residual B off. Okay, any question on this one? All right, our focus is on the last one, right there. You can see that since I did not simplify W switch, right? Remember, I could not do that because again, it would depend on the shape of the waveforms. So I'm just going to leave it as W switch. And as I said earlier, in order to find P loss, I could either divide by T, the equation by T, or multiply by F. And I chose to multiply by F to emphasize that now you see, to demonstrate that now you see the problem with PWM, right? What is the problem here? Anybody with PWM? What is the problem with PWM by looking at this equation?
If you increase your frequency, you increase your loss.
Exactly. That's the reason why I chose to use F, because now it's clear for us that the equation for switching loss in PWM is a function of F, right? And that's a problem, isn't it? Because theoretically, or ideally, I should say, we want to keep pushing switching frequency. Now you know why. One of the reasons why we cannot just increase, switching frequency if you use PWM. Well, number one, because of the limitation of the device, right? MOSFET can only switch at a certain max frequency. But in addition to that, you also have to realize that in PWM, if you keep increasing the frequency, you're going to end up with increasing the switching loss. Right? That's not good. Right? Increasing switching loss means reducing efficiency. Right? So this is things that you need to consider if you want to improve efficiency. Right? Things that you might want to consider as well when you do the design for your final project. Right? If let's say the efficiency of your design for your final project is it's only 85%, or I just need to push 2.5 more. Maybe, right, by reducing switching frequency, you can get it up to 87.5% to meet the requirement, right? So that's something that you can try, something that you can consider if you'd like to improve efficiency in PWM. Okay, is that clear, hopefully? Any questions on that?
I had a quick question.
Go ahead.
Generally, do you have the same energy loss per transition regardless of your frequency?
Okay, first of all, I try not to use the terms energy loss, right? It's more on power loss, not energy loss, right? Because we learned from physics that energy is conserved, right? So I would say it's power loss. And your question is whether or not this is true for any switching frequency, you said?
Yeah, like if the energy converted to thermal energy or
Right.
the energy converted to unusable energy is constant for any frequency.
From switching loss point of view, yes. Right?
Okay.
Strictly from this equation, yes. But keep in mind that loss because of power loss, because of frequency, comes into different shapes, right? Or comes from different sources, not just switching loss, right? So if you look at the overall power loss due to increase in frequency, it's not going to be linear. But if you strictly look at switching loss in PWM, then yes, it's going to be a linear function of frequency. Does that answer your question?
Yeah.
Okay.
Thank you. That's where I was going with it. Thank you.
Okay, yes. Yeah, especially when it comes to magnetics, right? Those are highly nonlinear when it comes to frequency, right? So the loss the loss due to increase in frequency, if you take into account magnetic loss is going to be highly nonlinear, right? But again, strictly for switching loss, it's going to be linear based on this equation. Right? It's going to be a linear curve if you plot switching loss versus frequency. All right. So makes it challenging. This last term, W switch times F, is linearly proportional to switching frequency, and that makes it challenging for us to use very high switching frequency in PWM. I believe the highest that I've seen for commercial product for PWM is 2 megahertz, maybe 4 megahertz. But it'll be nice to be able to push the frequency even higher, right? Why is that? Oh, right here. Those are the reasons. It'd be nice to have higher switching frequency operation. Why? Because we have smaller magnetic components, smaller transformers, smaller capacitance, right? And then smaller filtering requirements, meaning less current ripples, less voltage ripples, as well as a faster transient response due to increased bandwidth. So these are all the benefits that comes with higher frequency operations, right? So it'll be good to be able to use higher frequencies. But unfortunately, if you do that with PWM, you're gonna have to watch out for switching loss, right?
Professor?
Yes, go ahead.
So like you said, like the main frequency problem or why frequency is limited, like it's also because of power too. But isn't it easier to design high frequency inductors that have a lower inductance? And if you increase the frequency, you don't need as like large of an inductance, like the critical inductance becomes smaller. So like the components would be easier to have better high frequency characteristics.
Yeah, I think that's part of the statement that I made earlier, right? A smaller physical size of the magnetic components right there. So with higher frequencies, you get smaller magnetics. But I don't think I'm answering your question. What is the question again? Sorry.
So like, isn't the trade-off like a little bit canceled because you can use smaller components, but smaller components kind of allow for higher frequencies? Because like, isn't it like, doesn't it have to do with like hysteresis and stuff like that? I didn't take the course, so I'm not an expert in it, but.
Yeah, so I think the gain that you get is at certain value is going to be underwhelmed, I guess. What's the word I'm looking for? It's going to be not as much compared to the what do you call it, the cost that you have to pay, right?
I got you.
Yeah, it's always the case, right, with any design. Go ahead.
It's not like a direct trade-off, like one dominates kind of the other.
No, unfortunately not. Yeah, it is not a linear thing. So you're gonna have to find a sweet spot, right, when you're designing your magnetics, for example, or even other things, not just magnetics. At some point of time, your magnetic has to be operated at a certain frequency, beyond which, hysteresis loss or even the worst one, eddy current loss becomes exponentially higher than the previous frequency you use, as an example. So it's always a balance between that you're looking for, between these different factors for sizing the component, right? I'm not sure if I answered your question. Did I answer your question?
No, you did. Exactly. Yeah.
Okay. Yeah. And I think another thing that I mentioned is that components in general are limited, right, in terms of their frequency operations, like MOSFETs, right? MOSFET is limited when it comes to how fast you can turn it on and off, right? I'm not sure how fast currently MOSFET can be switched on and off. I'm guessing in low megahertz, maybe mid-range, 4 megahertz, around 4 megahertz type of switching, right? Whereas, for example, IGBTs, right? IGBTs is slower than MOSFETs. And that's why you don't usually see people use IGBTs for DC to DC converters, right? Because inherently you cannot turn the switch on, and you cannot turn on and off IGBTs fast, right? And that becomes worse when you use thyristors, for example, right? Or not thyristors, sorry, BJTs, bipolar transistors, right? So so that's another factor that you need to take into account when it comes to selecting frequency, switching frequency, the devices that you use, right? And then if you are concerned about the size of the DC to DC converter, then definitely magnetics will be the main ones for you to look at, as well as capacitors. Don't forget that capacitors also, the size of capacitor is also going to be a function of frequency, right? And I've not even touched, parasitics in capacitors, right? The one thing that we did touch in EE411 is ESR, right? Equivalent series resistance. And you can try this, if you get a chance after this class, go ahead and Google, ESR. You'll see that ESR is a function of frequency as well. Not only that, a capacitor also have what's called ESL, right? And they have a parallel resistance. It has series inductance, and all of these are a function of frequency, right? But how come we didn't consider those in EE411? How come it's just ESR? Well, because the answer to that is because the range of frequency that we are using for power electronics does not yet view the other parasitics to be important, right? This becomes important, ESL and parallel resistance becomes more dominant at much higher frequency, such as microwave frequency, Arakaki's stuff, right? But for us, TOFIC stuff, right? We are only dealing with lower, relatively speaking, right, compared to microwave. We're dealing with tens of kilohertz to lower megahertz. So for this kind of range, ESR is the most dominant. Higher than megahertz, gigahertz range, then yes, we're going to have to deal with the other parasitics in capacitors. And that could be the future, right? If power electronics, if the devices, technology, as well as magnetics technology can handle gigahertz, switching, then maybe someday when we in the future when we design power electronics, we're going to have to take into account ESL and then parallel resistors as well for the capacitor, right? So yeah, hopefully that answered your question. I'm sorry if I kind of sidetracking a little bit, but I think it's still related to this. Any other questions? No? All right. Okay. More about how am I doing the time? 24 minutes looks like. Okay. So now we know the problem with switching loss, right? In PWM, right? We're still looking at PWM right now, the hard switching, right? The next thing is let's delve into switching loss more, right? Before it was just all conceptual, right? There's an overlap, and there's a power loss because of the overlap. Now let's look more into this, right? Let's try to understand the behavior of this voltage and current of the switch during transition. Why is that important? Because if we understand how these waveforms behave, then the next step is to be able to attack this problem, right? Once we know how to analyze this behavior, then we can think about, okay, how do you, minimize or suppress this problem? How do you prevent, the overlapping to happen, right? But before we go there, before we reach this point, I think it's important for us to understand in more detail, how switching behaves, right? And that's that relates to what we call switching trajectory, right? So again, this is a concept that I believe is important for us to understand later, the solutions to minimize switching losses. Okay, so let's talk about switching trajectory. So switching trajectory describes switching transition behavior by looking at the positions of voltage across and current through a switch during switching transitions, right? Time or duration of switching transition is not represented in the switching trajectory, which is a drawback of this a tool. I should say this, this is a tool for us to understand switching behavior. Unfortunately, this tool does not show you the duration of time the transition is taking place, right? And so because of that, I'm going to use dash line when I'm drawing switching trajectory. I'm going to use a dash line for instantaneous change, and I'm going to use solid line for gradual change. Okay, so in order to understand what a switching trajectory is, I'm going to just provide you with examples. Let's start with the easy one, the one that comes from ideal switching trajectory, ideal switching transitions, right? We all know if it's ideal, then both voltage and current jumps, right? It takes no time for voltage and current to transition, right? Here you can see that's turn on and that's turn off, right? Turn on, you can see it takes no time for the current to go from 0 to high current. Same thing with the voltage, from high voltage to drop to 0. The opposite case is true for turning off right there. Okay, so how do you draw switching trajectory for this case? So please pay attention. This is how you would draw switching trajectory, and for sure you're going to see one problem like this on the first midterm. So what you need to understand are three things, right? Where does how does the transition begin? Voltage and current. And how does the transition end? Again, with respect to voltage and current. And then the third one, what happens in between, right? So 1, 2, 3, right there. So you need to know the starting point of the transition, the end point of the transition, and then what happens in between. Okay, any question on that? If not, let's try to draw this switching trajectory. Right. Again, as I said earlier, instantaneous, how do you draw instantaneous change? By using dash line. So if you see a dash line in the switching trajectory, that means it's instantaneous transition. Now, first of all, switching trajectory is a curve that you draw with the y-axis being the current through the switch, current through the switch, and the x-axis is the voltage across the switch. And then you map the transition on these plot right here, right? On this coordinate right here, coordinate system, if you will, right? So what did I say earlier? Number one is to know where the transition begins, right? So here, this is actually a combined curve. I'm gonna draw turn on and turn off separately. I'm going to do this slowly, just like I did in EE411. Right, first time I'll do it slowly, and then after that, it's going to go faster and faster. So I'm going to do turn on first, right here. Right, so this is turn on, this transition right there. Okay, where does this begin? Well, I know that this is V, this is I. The transition begins before I turn the switch on, right? So static condition, remember static number one, static condition number two, right? So let's say A, static B. So A is the beginning of the transition, or before you turn on the switch, right? That constitutes the beginning point of the transition. So you can see clearly from there that during static condition A, we have V off and I off. You see that? V off and I off. So V off and I off. I off is 0. V off is at a certain voltage. So 0 amps is going to be right here, right? And then let's say this is your V off, and then comma 0. Is that clear? So V off volts, 0 amps. That's the starting point, right? That's number 1, corresponds to this, right? So that's the beginning point. Okay, and then the next step is to look at static condition afterward, right? That's B right here. That's the end point of the trajectory. That's when the switching transition is done, right? You can tell that from that static condition, we have new values for current and voltage of the switch, right? You can see that the current goes to I on, some high value, and then V voltage across the switch goes to 0. See that? Voltage is equal to 0, I is equal to I on. So where is that on the trajectory? Where is it on this plot right there? Well, that's got to be somewhere here, right? So that's going to be 0 volts at I on. Any questions so far? So that's number 2. This step right there. So step number 2. Any questions? Okay, if not, the third one, this is the tricky part, right? Because this is where you have to understand how or how to plot during the transition, right? In this case, it's not that bad because you can see that during the transition time from here to here, let's say, you can see that voltage, or that, not actually, that's wrong, sorry. For ideal, the switching transition is right there, 0 seconds, right? Because it's instantaneous, 0 seconds. And so how do you draw that on the switching trajectory? Well, remember what I said, right? These are all instantaneous. If they are instantaneous, meaning you use dash line, right? So what happens during this transition? Voltage drops from V off to 0, correct? Drop from some V off to 0, while current at the same time goes from 0 to I on, right? At the same time, no time at all. I mean, 0 seconds, I should say. And so how do you draw that in switching trajectory? Well, since in the process it does not, right? This is actually instantaneous, right? From this point to this point. So theoretically speaking, it does not what do you call it? It does not go through other voltages, right? It's just going to go from V off and then boom, it goes to 0, right? Right away. So how do you do that? Well, from V off to 0, that's from this point, isn't it? From this point to 0, that's 0 volts right there, right away. So how do you draw that? With a dash line, like that. See that? That's a dash line. Good? That's the voltage. And then at the same time, what happens with the current? It goes from 0 to I on instantaneously. So voltage already done, current is also instantaneous. So that's another dash line for the current to indicate that current instantaneously changes from 0 to I on. Any questions so far? The last thing that I forgot to add here is number 4. Add arrow to indicate the direction of the trajectory, right? So if you look at this trajectory right here, right, where should the direction go? Well, it must be going from beginning of the transition to the end of transition, right? Beginning is number 1 right there, and is number 2. So therefore, the arrow should point from number 1 to number 2. So right here, like that. Any questions? No? No questions? All right. If not, then I'm going to do the other one, right? Turning off right there. Same way, I'm going to do, let's do a light color here. Turning off, same way I and V. I'm going to do it faster now, right? And You can see number one is to look at where it begins. What happened? Come on. There it is. Where does it begin for the turning off? Right here. Well, it begins right here, right? That's number one. And there's number two, the end, right? So you can see the beginning of the transition, we have I on and 0, right? I on for, let me erase this. See, I on is right here, right? And V on is right there, right? So I on and 0 volts. So I know that the beginning of the transition, we have this point right there. So that's going to be, what is it again? 0, comma, I on. So you can see that that is the same point as this. Right? So the end point of the previous transition now becomes the starting point of the next transition. Right? Does it always the case? Of course not. Right? Sometimes you have different currents, current that drops or voltage that drops because of the parasitic in the components or in the circuit. But in this case, we have ideal, right? And so for this case, they are the same, right? So the end point of the last transition becomes the starting point of the turn off transition. That's number one. What's number two? Number two is right here, right? So number two is V off and I off. I off being 0, right? So I know that at the end I have, that's your number two right there. The end of the transition, you have V off, comma 0, right? Some voltage at 0 amps. And then the third step right here is to determine what happens in between. As you can see, just like before, we have current and voltage that is instantaneously changing, right? From I on to 0, and then from 0 to V off. So again, use dash lines to indicate or to signify that the transition is instantaneous. And then what is the last one? Add the arrow, right, to indicate the direction of the trajectory. So in this case, since we are doing V off or turning off, not V off, sorry, turning off, right? So again, just like before, it goes from 1 to 2, starting to end. So therefore, the arrow should be this way for turning off. And this top one is turning on. Are there any questions on this?
I had a quick question.
Yeah.
Is there a reason why you just take it one at a time, current going down or voltage going up, and you don't just draw a line diagonally representing both happening at the same time?
Yeah, because if you do this, then it could be misleading, right? Because then you would say, oh man, that means during the transition, even though it's instantaneous, it has to go through those voltage and current. But you know, that's not the case, right? With ideal case, it's just like magic, right? It goes from 0 to right away, you know, without going through those voltages into that voltage. So instantaneous. Okay. Right? That's the reason why.
Thank you.
And then there's another implication that I'm going to explain, maybe not today, but later next week. Another reason why I don't draw it that way. Or maybe I could tell it now. Is that the area that is covered below this switching trajectory could indicate the type of switching loss we have in the transition, right? So if you draw it this way, right, this way, so you can see there's an area underneath, right? So it could be misleading as well. So that corresponds to, hey, we do have some losses here, even though that's not true, right? So, but if you draw it this way, the way I did, then go ahead and find the area under the curve, under the trajectory. None, right? There's no area under that trajectory, meaning there is no loss. And that's what we get from ideal switching trajectory. We don't have any loss at all. Does that answer your question, Nick?
Yeah, thank you.
Okay. Mm-hmm. All right. We have 7 more minutes, so let's see if I can go over the next example. right? Right there. Now it's no longer ideal, right? What happens here is that we have voltage and current that changes at the same time, right? You can see during on transition, voltage start to go down, and then current start to go up, right? This is just a made up example, of course. It could happen. If you have a snubber, you could actually get this kind of a shape, right? So same thing with the turn off transition. You can see that both voltage and current of the switch changes simultaneously, right, at the same time. And again, it takes time for both to turn on and off, right? So how do you draw this? Apply the same concepts, apply the same steps, 1 through 4, right? Know the beginning of the transition, know the end of the transition, know what happens in between, and then you add the arrow. Okay. So what is the beginning? Beginning is right here. If I look at the turn on transition first, that's the beginning. That's the end. That's what happens in between, right? So that's number 1, number 2, and then number 4 is just adding the arrow, right, from 1 to 2. Okay. So let's check it out. Okay. So beginning is V off and 0, just like before. N is 0, comma, I on. That's what I have. Oh, I combined both again, sorry. Yeah, you can actually combine both, just like I'm combining this. I forgot to mention, sorry about that. So I'm combining both switching trajectories into one. So you can see, how do you do that? How do you combine the two? Well, because the two shape the same way, right? This point happens to be the same for turn on and off. Same thing here. This point happens to be the same for turn on and off. Same thing with the trajectory. Happens to be the same for on and off. The only thing that's different is the arrow, right? For turning on, the arrow goes from off to on. So that's why I'm labeling one of the arrows to be on, to signify that for on transition, it goes from here to here, right? That way, right? From here to here. Whereas for off, it goes from there to there. Okay. Any question on how to merge the two? Okay. If not, let's look at this one right here. Let's just do the on time right here. And then you can do the off time yourself. Oh, that's I. This is V. All right. Beginning, just like before, right? You have V off and I and 0. So that's, let me use a different color here. That's your number 1, your beginning point, right? And then the end point is right there, just like before. Yes? Any question on that one? All right, number 3. Now it's no longer instantaneous, right? Now you have to, basically plot, point by point. Have to find this point and that point, this point and that point, right? Or here you just need to just do what do you call it? Find one point, because you only need 1 point to complete the trajectory for this one, because these are all linear, right? And sorry, in fact, you don't really need another point, right? Because these are all linear changes, so we know it's going to be following this trajectory. It's supposed to be a straight line. You get the idea, right? It's supposed to be a straight line because both are linear, both are straight lines, right? So it's going to travel from number 1 to number 2, following linear transition like that, right? And the arrow goes from 1 to 2, right there. Okay. Now we can double check, whether or not this is true, right? You can see that as voltage goes down, that's over here. Let's say that's point A. You can see current start to go up, right? So that could be this point right there, right? As the voltage goes down, current goes up, right? If you look at this point, right? So voltage goes down, current goes up, right? And then another point, let's say over here. Let's call it point B. So you can see that, current keeps increasing close to the final value, whereas the voltage now close to 0. So that could be corresponding to this point right there. right? That's another trajectory point right there. VB, IB. All right, any question on this? So if you do the turn off, it should be the same way, except it's the arrow is going to be the opposite direction. That's why when I combine the two, you get this picture right here. Right? Yeah, you could do what is it? Off state, on state, right? So you can do. We know by labeling it this way as well. So I'm showing you a different way to merge the two. Instead of labeling the arrow, you can also label the points. So off state, on state. So we know that if it's turning on, it must be going that way, right? If it's turning off, it must be coming from on state to off state, right? Or you can also do the other way, right? The first way I showed you, right? You can label the arrow. This is going to be on. That's going to be off. Right? Same thing. All right. Now realize that after I oh, by the way, you have to use solid line, right? Not dash line anymore, because it's not instantaneous. Notice that there is an area under this trajectory, right? So this corresponds to some loss. Unfortunately, we don't know what that loss is, because why? Well, I'll tell you why. Tell me what happens with this switching trajectory, right? Now you know how to draw this for this transition. What happens if I do this? And then we can adjourn after this.
You have to know how long it's going to be state.
Yeah, but before you already answered. But what happens if I change the switching trajectory? Sorry, not switching trajectory. Switching transition to this. So there you go. Different slopes. What do you think is going to happen with the switching trajectory?
Nothing.
Nothing, right? It's going to stay the same, right? It's going to remain the same. So it's going to look like this again, regardless of how long the transition is. And that's the drawback of switching trajectory. Do not try to calculate switching loss from switching trajectory. This is just to show you how the switching waveform behaves during the transition. And why is it important? It has to do with what we call SOA, safe operating area, which we're going to talk about next week. But when it comes to switching loss, you cannot calculate it from here. But you get an idea by looking at the area under, right? The bigger the area under the switching trajectory, the worse the loss. We don't know what that loss is, but we get an general idea of the type of loss you get. So, for example, if the area is a square area, like the next one right here, right? Yeah, see that? And then you can see that, oh, this is going to be worse loss than the previous one. Okay. Again, we don't know what that loss is, but at least we get a general idea of the type of switching loss we get compared to other switching trajectory. All right. Oh my God, it's 10:31 already. So sorry. Any questions on this? No? So please do the rest of the examples yourself. If you have any questions, let me know. We have the rectangular commutations, right? We just went over 2 examples, and I'm going to ask you to do the last one for you to do yourself. Any questions? No? All right. If there's no questions, then we are done for the day. Have a good weekend. I'll see some of you later today. For the rest of you, have a nice rest of the day and have a great weekend. Bye-bye.
Bye. Thanks, Professor.
Bye.
Thank you.
Bye. You're welcome.
Professor.
Bye.